Hey guys, how's it going? I'm the tropical teacher, and today I'm going to teach you about differential equations. But of course, I can't do it alone. I have my faithful assistant with me, Dr. Dog.
Hello students, what's up?
With both of us teaching you guys can bet your britches you'll learn differential equations faster than you can say coconut. So what exactly are these differential equations we'll be talking about? Well, a differential equation is simply any equation that has x, y, and derivatives of y in it. You can use them for various problems involving concepts such as radioactive decay, population growth, or if you're Mr. Milos, torturing the souls of young students. In addition to learning just what the differential equation is, you'll also learn how to use initial conditions to find out the particular solutions. Approximate these particular solutions with sloped fields and Euler's method. Alright, let's get down to business. A function f of x is called the solution to a differential equation if you can satisfy the equation by replacing y and its derivatives with f of x and its derivatives. Take y equals x times e to the negative 3x, for example. It's the general solution to y prime plus 3y equals 0. We know this because when you plug it in, you get 0. Remember, y and f of x are the same for these kinds of problems. One property of differential equations is their order. The order determines how many arbitrary constants the equation has, and is determined by the highest order derivative. For example, s double prime would be a second order differential equation, and v prime would be a first order one. As you can see with x double prime of t equals negative 12, the general solution would take the form of negative 6t squared plus c sub 1 times t plus c sub 2. This is because we need to take into account each constant we lose through differentiation. This brings us to example 1. To verify the solution, just make like Glade and plug it in.
Freshness with a spin, plug it in, plug it in. Mr. Johnson, family company.
Let's try it out with the equation y prime plus y equals 0. Among these, which are solutions? We can tell that the first one is because you end up with negative 2e to the negative x plus 2e to the negative x, which ends up giving you 0. When you try out cosine, you end up getting negative sine plus cosine. And even a dog can figure out that doesn't equal 0.
Hey!
And the last one also works, because negative ce to the negative x plus ce to the negative x equals 0. You should notice that the two that do work are of the same form, and in this case you can use any constant for c. Now we'll move on to particular solutions. But Dr. Dog, what's a particular solution?
A particular solution occurs when you are given initial conditions.
Thanks, Dr. Dog, you're the greatest. So since we learned that for y plus y prime, that the general solution was c times e to the negative x, if it said that f of 0 equals 3, we know that the solution is only satisfied when c equals 3. Let's try it out with the new problem. For the differential equation x times y prime minus 4y equals 0, verify that y equals cx to the fourth is a solution, and find the particular solution satisfied by the condition that y equals 4 when x equals 2. Well, when you plug in cx to the fourth and its derivatives where y and its derivatives are, it works out perfectly, so you know that it's a solution. Now to solve for the initial condition. Just figure out what c is, and replace it in the general solution. So now we know that the particular solution is x to the fourth over 4. Neato. But Dr. Dog, how do we get these solutions?
Well, it's simple. All you need to do is draw a slope field, or use Euler's method.
So, slope field, you say? I guess those would be useful. With them you can solve differential equations that might otherwise be impossible, because you can sketch short lines of the slope to see the graph of the function. What does a slope field look like? Let's find out. First we should write out our values in a chart. Once we have those, graphing the slopes will be cake. The graph shown is obviously filled with more lines than you found, but you only need to plot until you can find the pattern. Now that you can graph them, can you match them? Remember, slope fields are simply the tangent lines at any point. Since for the first one, everything along the y-axis is 0, we know it has to be the graph of y prime equals x. The same is true for the second one, but along the x-axis, so it's the graph of y prime equals y. And the third graph pretty closely resembles the graph of e to the x. Coincidence? I think not. Now to figure out which graph is a particular solution. Let's try the graph of e to the x again, this time with the condition that it passes through the point 0, 1. All you have to do is trace the curve from that point. So now you know everything there is to know about differential equations, right? Wrong. Here comes Euler to haunt you from his grave. Euler's method is the numerical way of approximating solutions, and while it does take a bit longer, it's a lot easier because you're just plotting points on a chart. To get the x values, you just add the designated step h to your last value. For the y values, it looks a bit more complicated at first, but notice that it's basically y equals mx plus b, with the previous term. Now for our last example. Using the formulas I just gave you, make a chart for the first 5 values of x and y. Once you have that, you can plot your points. Now you see the beautiful graph you got on the left? Depending on the size of h, it's probably a lot smaller than it looks, but here's your answer. So what exactly did we learn today? Let's go through it one by one. First up is differential equations. What exactly are they? They're simply an equation that has x, y, and derivatives of y in it. Next in line is solutions. Solutions to a differential equation are any function that you can substitute for y into the equation that allows it to remain true. The order to a differential equation is the highest order derivative in said equation. What does that mean? All it means is that a fourth derivative of an expression has a higher order than the first derivative one. Initial conditions are given statements that allow you to determine any arbitrary constants you might have accumulated through differentiation or other means. Using these initial conditions with differential equations, you can solve for c. This allows you to eliminate all arbitrary constants in your general solution and get the... Yup, you got it, particular solution. Now to find these, you have to use slope fields, which have you drawing a bunch of tangent lines to sketch out the graph of the function. And finally, Euler's method is when you use tiny steps h to slowly predict the direction of the curve. So you might be saying to yourself, when does this ever get used in real life? Well, slope fields can be used to determine the direction of the force that charged particles exert on each other. I don't know about you, but I can't walk out the house in the morning without thanking the geniuses that invented this. Euler's method can be a pain, but sometimes it comes in handy. You can use it to approximate the trend of a curve over short terms with it. You don't want to go too far, because then your error will just keep compounding. One example would be to try calculating what the national debt would be in a year or two. Makes you realize just how little money we actually have, don't it? Let's go over a few more problems, this time a tad harder. Here we need to see if y equals 1/2 x squared minus 2 cosine x minus 3 is the solution to y prime equals x plus sine x, and afterwards verify that y of 0 is equal to negative 5. Alright, so first, all we have to do is find y prime. When you take the derivative of the expression, you get 1/2 times 2 times x plus 2 times sine x minus 0. That simplifies to x plus 2 times sine x, which is what we need. Bingo. So now that that's down, let's check the initial condition. All you need to do is plug in 0, and voila, you get negative 5. That wasn't so bad. Now on to another slope field. For this one, we just have to determine the particular solution by solving for c. When you plug in 0, 3, as the point on the graph tells us to, you get c equals 3. So plug in that 3 back into the initial equation, and there you go, you have your particular solution. For our last review problem, we'll practice Euler's method once more. Use Euler's method to make a table of values for the approximate solution to the differential equation with the specified initial value. Use n steps of size h. Simple enough, right? When you plug in 0, you get 0 and 2. 1 gives you 0.1 and 2.2. The second n value gives you 0.2 and 2.43. The third gives you 0.3 and 2.693. Fourth gives you 0.4, 2.992. 0.5, 3.332 for number 5. And 0.6, 3.715 for number 6. And we're done.
Yo, Dr. Dog here, and I got a tune about differential equations and what you gotta do. If you're stuck with a radioactive decay, it ain't your lucky day, and if you need to find the population growth, here's what I gotta say. Find the solution. It's the only resolution. There's two different ways to make a child's play. First you take the slopes and you draw M in their field, the resulting graph. Your answer will yield. And next is Euler's method. You use steps to make a chart. Once you have that down, what you graph will look smart. Always remember kids, slope is dope. Now Dr. Dog here. I hope you liked my rhyme. Gonna sign off. I'll see you next time.